All right, we're looking here at vectors, and what basically a vector does is allows us to go beyond just a standard one-dimensional idea. So for example, we talk about speed in your car. Speed in the car, whether you're going in drive or whether you're in reverse, your speedometer still will tell you the exact same speed, whether you're going 20 miles an hour forward or 20 miles an hour backwards. What vectors allow us to do is to give not only a magnitude, so how fast you're going, but also the direction. So they can tell us, you know, for a car, easy, forward, backwards, but really you can go in all 360 degrees in terms of what direction you're going. That's why we like the idea of vectors. Okay, so basically, the way we look at vectors, well, you have a starting point and an ending point. That's the easiest way to identify these. So for example, this vector, which I'm calling V, and it has this little kind of half arrow over it, that's how you symbolize a vector being used, is with that notation right above the V. Basically, the easiest way is with this line segment, and what this does, you have an initial point, so where you're starting, and you have a ending point, a terminal point. So you have to start somewhere, you have to end somewhere. That's how you come up with a vector. And with that too, vectors all have a magnitude, or what we call a length in this case. The way we identify length, it almost looks like absolute value sign, kind of a double absolute value sign. That's just the notation that we use. But basically this is saying, okay, I started at point P, so I started at the park and I ended at point Q. I ended at the school. You would have a magnitude, so how far you went, and the direction of obviously which direction that you went. Okay? So the way we graph vectors, what's really nice is that with vectors, it's almost another way to think of it would be like a force. So for example, I have something sitting right at the origin, and I have two vectors here, calling them u and v. This is like somebody's pulling up and to the left at that force, somebody's pulling up and to the right at a much stronger force with vector v. When you're graphing vectors and finding what we call the result of these forces being put on an object, that's when these are most often be used, especially like in a physics classroom. What we use is something called the tail tip method. So for example, if I want u plus v, I'm literally going to draw u, and then I'm going to draw v, but instead of starting at the origin, I'm going to start from where the previous one ended. So that's u plus v gives me the result, which I'm going to draw here in white. That white arrow is u plus v as your resultant. So as you would possibly expect, it should be a little bit further this way because you have the other force of u being acted upon it. Okay? Negative would work just like you would think. So instead of going v in its normal direction, you'll go the exact same but in the opposite direction. It's almost like you flipped it completely around. Let's do this one here. 3u, well, if here's what regular u looked like, same thing. 3u would just be 3 times as strong. Just that simple. So it'd be like if you put u on top of itself 1, 2, 3 times. I actually did that relatively accurately. And this last one, u minus v, well, really, you should be thinking of this as u plus negative v. So same idea with the tail tip idea. You go u, and then I would go, well, here's what negative v looked like. So your resultant would be going back from your original to where you finished up. That white arrow is u minus v. Okay, so what we're going to use a lot with, though, is what we call a component form of a vector. And it looks a lot like an ordered pair. Now, you don't want to say component form as an ordered pair. That's a big no-no, because that's just exactly what it is, something on a coordinate plane. But basically, it should look like, well, it's very similar. You have x values and you have y values. So essentially, this would mean that I'm moving 1 in the x direction and I'm moving 5 in the y direction. Doesn't mean I'm at the ordered pair 1, 5, but it means that I've moved in that direction. So the way we use with finding a vector, well, if we have that initial point and that terminal point like we had in the previous slide, well, we can find your change essentially. This is essentially a change in x and a change in y by doing a subtraction. Final minus initial. So your final x value and y value, or your final x value minus your initial x value, and then your final y minus your initial y. Final minus initial will give you your change, and that's how you find your vector. Okay, so here's an example. To find the component of a vector v, that should have our line over it, that has an initial point of 3, -6, and a terminal point of -2, 4. So what we do is we're going to find the vector. We use these arrow brackets to represent them as a vector, and all we do is we subtract the x values first, so final minus initial, and final minus initial for the y values. Back when we did slope, it didn't matter if we went, this being 1 and this being 2 or vice versa, because you had the slope that would cancel it out. You need to make sure you do final minus initial. So your vector here is -5, 10. Okay, now what is the length of vector v? So meaning, what is the length? The way you find length is actually very simple. If we think about where this looks on a coordinate grid, -5, 10, essentially what that means is that your vector, if you had started at the origin, would have gone an x value of -5 and a y value of +10. Well, I just made a right triangle. This value is -5, this value is 10. How am I going to find essentially my hypotenuse there is with Pythagorean theorem. So the length of v, and here's your notation with it, is just going to be the x value squared plus the y value squared from your vector. That would give you technically length squared. A squared plus b squared equals c squared. So I need to take the square root of that value. So this ends up being the square root of 125, and you can simplify it if you can. I'm going to leave it just like that. Okay, here's one for you to try. So at this point, please pause the video, see if you can find the component vector and the length of this vector from initial point 3, -2 to the terminal point -1, -4. All right, let's see how you did. You should have gotten, if you started at 3, -2 right here and ended at -1, -4, there's your component vector, -4, -2. Again, make sure you go from final minus initial for both your x and your y. And then to find your length here, you took your x value and your y value from the component vector, squared each of them, took a square root. If you left it as square root of 20, that's fine. If you simplified it as 2 square roots of 5, that's awesome as well. And the last thing I wanted to mention, something called a unit vector sometimes comes up. This is actually really big right now for like a SAT, or maybe not even SAT, but like college prep tests. Unit vector, all that means is you take your vector, if you divide it by the length of the vector, then you're going to get a vector that is exactly 1 unit in length. So what would happen here is that, well, instead of being this whole big long arrow, it's just guaranteed to be exactly 1 unit. So all we did is take that vector, -2, -4, and we divided each of them by the length, the 2 square roots of 5, and that's how you get your unit vector. Well, there you go. There's a crash course on vectors. We'll look at finding component forms and breaking down back into x and y components in our next video.